Have you ever wondered about what are the most basic ingredients that make up our universe? That's where particle physics comes into play. Particle physicists created a remarkable recipe book that describes the tiniest constituents of matter and their interactions, brilliantly called the Standard Model. These elementary particles are thus organized into fermions, such as quarks and leptons, and the first mediators called the bosons. While this theory has been incredibly successful, there are still mysteries in the universe it cannot yet explain. To achieve these answers, the CERN's Large Hadron Collider was built. It is the world's biggest and most powerful particle accelerator, and it is able to recreate conditions similar to the ones shortly after the Big Bang. In one of its colliding points there is the Atlas detector, which operates as an elaborate camera storing clues about particles that originated in such collisions, such as their mass, charge and speed. One of the main focuses of the LHC is then to search for new physics beyond the Standard Model. The bulk of the current searches, however, is model-dependent, meaning that they test the probability of encountering a signal that differs from the expected Standard Model. Although these searches are of paramount importance, they are limited by the fact that they are only sensitive to the models that they are designed to test. My master's thesis will explore a model-independent search for new physics, anomaly detection, with the implementation of weakly supervised machine learning methods that are only trained on Standard Model background and thus are expected to flag new physics as anomalies. One of these models is the autoencoder. The autoencoder is a neural network with a very specific architecture so that it aims to reproduce its input. It starts by encoding the data into a smaller dimension in an intermediate layer, called the Lardon space. The encoded data then goes through symmetrical decoding layers in order to obtain the reconstructions of the input. As the autoencoder is only trained on background, we expect it to provide poorer reconstructions of the signal events. Therefore, the reconstruction error can be taken as an anomaly score. In order to study the feasibility of data-driven models, there is the need to train models that might be robust to systematic uncertainties present in the experimental data. The adversarial autoencoder is a more complex model composed by a reconstructive autoencoder and then a discriminant neural network. The autoencoder operates as I explained before, except that its inputs are Standard Model data with different sources of uncertainties. The inputs of the discriminant neural network will be the element-wise reconstruction error from the autoencoder. It will then be trained to distinguish between the classes of the background data. In addition, the models will be trained adversarially. Therefore, the autoencoder will be penalized by how well the neural network is able to distinguish between the datasets from its reconstruction error. This is done by training the autoencoder with the objective of minimizing the mean squared error as usual, but subtracted by the loss of the discriminant weighted by an hyperparameter alpha. My goal is then to achieve an autoencoder that is able to reproduce the background despite its systematic uncertainties, and that later on is still able to identify signal anomalies.